No, yeah. A few images that was lost, but but many of the indexing methods, they are trial and error, mostly error, or in principle only error. But that's the good thing with computers; they don't hesitate to calculate. Don't calculate fast, and they don't calculate accurately unless you use integer arithmetics. But they do calculate, and then nowadays they're seemingly quite fast, but depends on problem. I mean, a trial and error method is perhaps Monte Carlo. Try some random unit cell parameters and see if it fits. Change some of them in a Monte Carlo point of view, and maybe evolve these unit cell parameters, some kind of algorithm, genetic algorithm. Fancy word nowadays. We have a program that is sort of Monte Carlo based. It's the Maillet. I don't have very many examples of that. We can try it. I don't have any genetic program, but there are probably one or two available that you can find on. There has been attempts to use a Patterson-based method, make a radial Patterson. Maybe that is more of a structure solution. These different methods, they could be manual. And I have a couple in the end here. We can try to solve some indexing manually, with the help of a calculator, or use some automatic. Normally, we don't use manual method, but it's never wrong to be able to follow the procedures in the automatic program. The trial and error. The trial and error could be done in various spaces, either in HKL space or in ABC space. I mean, typically for reals. But I mean, both of them are principal trial. These are usually sometimes nowadays software and have some also. If you sit down and try to index a pattern manually, maybe you need some information about it. Maybe from the direction pattern, if there is few, maybe you can guess that there could be a high symmetry. And if there are a lot of people, then it's probably good. And you also know that low angle reflections, they have small indices. They are close to the origin. Next time. One of the softwares that maybe the software that I'm most experienced in is the Prior software. It's a trial and error method in index space, meaning that yes, for some HKL. Suppose we have a set of base data. X, B, 0. Okay? Then we can select a couple of them. How many do we need? Yeah, it depends on the symmetry. But say that we have a 2-parameter crystal system, tetragonal or hexagonal. bigger now. So suppose that this line to have some indices H1, K1, L1. We don't know which, but we know that they are small because it represents a line that is has a large d value. Close to reciprocal space. Then suppose that this is another line. If these two are not linearly dependent, then we can solve for the unit cell parameters if this would happen to be correct. And with a computer program, we can, like Theor, for example, can generate HKL and select some baseline, and then we get the cell parameters. These are lowercase p. But is this a correct unit cell? Yeah, then we need to check. Is it possible to index all of the rest of the lines with this unit cell? Probably not. That is the error. And here, then the computer just tries another HKL, solves another unit cell, checks. Oh, sorry, not again. It's still error. And the error comes out that only a few of the lines could be sort of indexed with the parameters. So maybe we made the wrong choice of baselines. Maybe this one is linearly dependent. Maybe we should select another one. There are a lot of different procedures how to vary the selection of baselines and also how to vary the indices. If you do it completely general and completely exhaustive, it will after a while take a lot of time. Suppose that things happen for you have 6 parameters. A, B, C, alpha, beta, gamma. And what is the maximum value of an index for the initial lines? Perhaps 2? No, wait, no. Or that means that 0, 1, 2 is a possibility for H. And K is perhaps then, unfortunately, also the negative needs to be done. And L also for each line. So this is 3 times 5 times 5. This is 75. 75 combinations raised to the power of 6 times a few possibilities for generating different baseline combination, and this is just a possibility. 75 power of 6 is something like 11. Now it starts to become quite problematic even for a fast computer, because 10 to the 11 number of times 6 equation seems to be solved just for generating individual each the possible unit cells. Can be done with a fast computer. Limit stuff is usually try to limit these index values very much. That will perhaps give a considerably smaller amount of trials, so it can be done in practice. But practice, respecting it can take several hours, tens of hours, hundreds of weeks, depending on what computer you have. More or less all indexing programs, they are the old-fashioned serial programs. None of them, as far as I know, are heavily parallelized. They can't use a machine with 10,000, unfortunately. But still, except for triclinic, that is worst case, or say orthorhombic and monoclinic, it can usually be done within seconds on a normal level. Maybe because when the indexing program finds a solution, data doesn't go through all the different possibilities. We need some criteria of whether it is good. There are a couple of them, but the classical ones are M for merit, F for merit. That's not me. They call the figure merit and higher. And question: could you allow unlimited lines? If you have a lot of, say that you have 20 lines, how to explain that? If you can, then it's okay. I'm sorry, I forgot I had sodium chloride a mixed sample. And if you can explain the unindexed lines, then it's quite okay. It could be an unknown impurity. But if you think that your sample is phase pure, then all lines need to be indexed. Otherwise, not a unit cell. Depends on what criteria you. Some lines, they could be irregularly shaped and such things, so it's difficult to tell where the peak position is. But if you allow some sort of range of acceptance window for each reflections, still they are unindexed, then it's something fishy. I guess either you have impurities or you haven't solved the problem. Perhaps time for the microscope. Several phases that has been tried various times that you can index multi-phase samples, not with the classical methods of generating a lot of indices, except for the high mixing two triclinic patterns. I don't. No one will solve that. Those at least. Perhaps you can allow a lot of, if you have a two-phase sample or several phases, if you allow a lot of lines, that still finds a very high figure merit for a subset of that is perhaps a way to find the cell in a multi-phase sample. But that requires, on the other hand, that you have very, very high accuracy of the peak positions. Can get that from a fancy state-of-the-art diffractometer synchrotron, but hardly from an in-house machine. Even with the modern machines, there are still limits to the accuracy. Someone leans at the detector and then that was the TREOR. And the base for TREOR is that generate a couple of HKL for the lines. And then that you tell for it. Wait, 1035, no problem. Another trial and error method is implemented program called dichotomy of volume space. Dichotomy is cutting. So we have a say unit cell. Suppose this unit cell is chopped up several different times. I think 6 times, or equal starts with say a plus 0.5 angstrom or something. The size of this original unit quite small, but suppose we have a plus minus delta A and B plus minus delta B, etc. We can define we can let the door open maybe. There was one. Yeah, there is. Let the door be opened. Hey. We have key cards for you, all of you, at the expedition. At least that was what Ken told me. So if they are ready, you should check that in a house. I can show you. Vad var vi någonstans? Diktor. If you have a unit cell or plausible unit cell with some error limit, then perhaps with these error limits you can sort of max for each of the observed lines, generate a lot of HKL, will give Q mean and Q max. Is it possible to find approximate then HKL first line, perhaps that one? Could be several HKL, and that is unfeasible, of course, but better with too many than too few. And then we make a dichotomy. Chop this all up into slices and repeats this process. Now, I think all lines index by one of those small unit cells, set of unit cell parameters with quite small error limits. Then we say that then it's okay, and go for refinement of the cell parameter. Refinement is rather straightforward. It's more or less a linear least square process. It can be done as long as we have the starting unit. Easier than refinementing crystal structure refinement, because then the content of the unit cell could vary quite a lot, and we need to do repetitive unit cell or a crystal structure refinement, like in the square cell. But with the unit cell refinement, it's usually one shot and everything fine. The worst case, there could be some non-linearity to change unit cell, the HKL values. If the unit cell is refined to considerably different position than the starting position, then maybe the HKLs are changed for the lines, and then we will have a oscillating refinement, but less of a problem compared to structure. Otherwise, equal is same as 3, or you need to check it. Also, between the whole line in some And if yes, then we found that Dicol is and the versions of Dicol we have available, they are exhausted, and we say that unit cell is A, B, C should be from 5 to 25 angstrom. It will try, I think it's divided 0.5 angstrom steps, try all possibilities. And some sense equally better choice than prior, because it will definitely visit all possible places, real space. The bad thing with Prior or the disadvantage or with Dicol is that it takes time. It can easily take days. Even the modern computer. On the other hand, it doesn't matter. Certain machine to start a calculation when you go over, then it promises if there is a have to and the unit cell, how the unit cell parameters of the lattice spacing are described. Complicated expression, I think. For cubic, it's quite much simpler than from the general triclining. Horrendous. We have a couple of images later. This is the traditional way of presenting the 1 upon d square. This is what I call Q. And here you can see it is we have the real space parameter A and C, spelling clinic A, B, C. Now let's see where is it? Beta, gamma, and alpha. All of them are contributing values. And I recommend expressions, but maybe it could be good to see that they are similar. It's simpler if you define it in terms of reciprocal space unit cell action. Will do. Different errors that could occur. For example, at the erroneous height, or if you have some heavy absorption in the sample, then even with transmission measurements, you could have a displacement of peaks depending on absorption. Could have 0 point errors, mechanical 0 point errors from the diffractometer need to be calibrated so that when it says that this angle is 10.23 degrees, then it is actually 10.23 and not 10.25, unless you want to allow for error limits, large error limits. One can say that if you have too large error limits, then maybe one should say that they have low accuracy in your peak position. And there is a saying that structure analysis that could be done on lousy data, but not indexing. You will find an answer, yes, also hundreds, thousands of other answers. So that's a problem. Better to avoid errors. Easy to say, less. Here is an example of barium sulfate, where it not enough large errors positions. All of the dots are the third degrees in theta. On the wafer is usually we have a so-called zero scattering silicon wafer. What is that? I asked the first time I was encountered that this feature. Yeah, it's a piece of silicon that does not scatter X-rays, they told me. But this is impossible. Really. But it didn't. So you need to write. You put a sample, it's only the sample that scatters. And the reason for that is still there are still some atoms, but there's still single crystal. So why doesn't it scatter? It's because it's cut in a direction where there is no reflection, at least out in the copper sphere, within the copper sphere. But if you put this one into a silver radiation, for example, with the 0.5 angstrom resolution or wavelength, then you actually that far out in reciprocal space not to scatter. Unless you have silver, you won't recognize it. And with copper radiation, very, very silent. Normally, the thermometer is very, very well calibrated. The surface of the wafer is the perfect position. But if you put a sample on, then it's too high. Oh, error, but still index the pattern. So if it was barium sulfate, then we do what kind of indices these allow for large error limit. But if we wouldn't have known that, then we would perhaps allow 0.1 degree error limits, then that is very, very large. Perhaps we would have found it, but maybe not. So this is the third, where we do the square refinement of the unit parameter. Then they change slightly. So the errors and compensate for the error. So get the green dots is square wafer data. It's still not excellent, but perhaps we have got the parameters compared to the square refinement there instead of the correct. They were filling up a small cavity, and then maybe with a sample holder upside down, backloading, filling up. So the correct position is here, and the surface of the sample is also well in line with the correct position, and with the back holder there, that we got the red position. Here you see that the average, well, the deviations are plus minus 0.02 degrees. But it's much, much better and less varying than putting them on. It's quite common that people try to but more something should, of course, scatter more. Yeah, I can understand. But you will also get the 0 point error or a systematic error. That will actually vary also with data. That line. But while if you don't have a systematic errors, then there should be no constant random error nearly go in the backlog. Now clock is 10:51. Should we have a short break? Five minutes? Leg stretch? 5-minute leg stretch, also for you on Zoom. If you sit in a chair all the time, it's not so easy to come up with coding. Yeah. What to do if you have errors? If you only have a silicon wafer and you don't have enough sample for filling up a large backscattering or a backloaded sample holder. Understand, or in the last view graph, I say, or otherwise get a fancy cost money. And this is perhaps takes in some internal standard. That is, for example, silicon powder. You know where the peaks should be with silicon. And then even if they come at their own spaces, it's quite easy to identify this peak and this peak is silicon. And you can correct for misalignment all different ways. And if the standard sample peaks from the standard sample, they overlap, then you perhaps to record another sample. But then you can use the other peak sample as standard peaks and correct the other lines. Or use very fast. And then you need samples from the past, from the previous millennia. Here is a sample with of calcite, I think, photographic coding. But then we mixed in some silicon, and this is a line for silicon at 28.44 degrees. And here's another line, but this overlaps. But we still was quite easy to identify that this is silicon line. Then we can compute a correction curve and then apply that correction to the other sample line. And we would get the accurate position of the other lines. Disadvantage is that perhaps you do measurement or pollute your sample with the internal standard. And perhaps it doesn't solve all difficult problems. You are interested in very, very low order big positions, then it's difficult to find standards that have those ranges. Silicon, for example, has the first peak of 28 degrees. If all of your interesting are before 28, so perhaps not a very good solution. You need some other. Why is still low? And these parameters that are from the initial calculations, if they are slightly erroneous, then they won't fit the rest of the correction path. And then you will miss the possibility with that this is perhaps not the correct unit cell. With equal, you wouldn't have that problem. Find enough large ranges of the error limits here, then it would in principle find the answer. But lower the line, if this is, we have some height error, then high order lines, then it doesn't matter if something here or here, very small, the data position will be more or less similar. But if you have a low order line, then it better like that, or quite a large error. So when measuring a powder diffraction pattern, the peaks that are necessary to measure accurately are the low order lines, but they're also the most difficult one to measure, at least with height error. You can try to correct that. There are software that have the only finding a unit cell, we can refine it. It's a simple least square procedure for refinement of the parameters. Can possibly make it linear or non-linear, but it can be done with a linear model, so why not that? If we define it in terms of AB, then it becomes non-linear. But maybe you need to have some extra parameters, zero shift or height shift or zero shift or 0-point error. Then that is perhaps non-linear component, or we need to some approximation. Maybe a linear refinement, and then with large error limits, then trying to find the 0-point error, and then a repeated linear refinement until we will get the self-consistent result. There are a lot of programs available. The one in HiScore works quite well, I think. It could be very non-linear if the indices, they're not unique, or if they change. If we have a unit cell and we have a set of diffraction lines, refine the unit cell and then the set of indices, if they change, then you're into trouble. Need to have some kind of damping, maybe, but this is a problem. Some software managed to solve it. That should be damp. And for this Australian problem. Not Jana, the Coelho. It uses a numerical procedure that is probably the most stable available. So. Anyway, maybe you don't find the correct answer, but at least you're able to drive it. Perhaps one should, if you know crystal structure, try to systematic conditions for reflections. Don't allow the to generate one. HiScore, you can select the space group or something like that, and perhaps that is used also in the refinement. The space group determination procedure in HiScore is perhaps not optimum. You will get a lot of choices. Conclude. Based on low angle lines, try to solve Unicell parameter. This is from a manual box. And if you can index most of the lines, then do some least square. Approximately the same is procedure in DeepL, except that DeepL doesn't generate a lot of HKLs. Reciprocal space takes real space and a small domain with approximate Unicell parameters. Is it possible to index? If it is, then it makes dichotomy of that small domain and tries the smaller part until it finds either it finds a very small one that is able to index all the lines, or may fail. If it finds a domain that takes all lines, then it goes to least square. And background for how the diffraction, the indexing process works. The distance of a reflection, now we are in reciprocal space. I indicate that R here. And the distance is the index is HKL. Scalar with the A star vector, B star vector, C star. These are the reciprocal space vectors. So the D value, the range, the distance from origin to every possible reflection space, we call it D star, or we could say R star. Then define another thing. This is a vector quantity, and maybe have a purely number or a scalar. Then we can take the size of it and square it, for example. The size, maybe we should need to square it. This is from history, actually. A vector square is usually done by a vector times the vector, row vector times a column vector, or the opposite. And then we take transpose the vector. So essentially that one, but second one should be like that. That's it. So this one is the HKL scalar with a T, and the other one the transponating. Then we change positions, and horrendous formulas, but formulating this Q expression, the D star times D star transponate, we can reformulate it like that. Here suddenly there is a matrix appearing, a matrix defined by the reciprocal space Unicell constant. This is called the reciprocal metric sort of transformation matrix for a vector HKL to another vector HKL, which happens to be the same, but it's at least a row and column vector. One can express it in the reciprocal space unitary parameters like that. We don't need calculations manually, but we could perhaps put some background. So Q value can be expressed like HKL times the matrix here and the column vector. So we should express this as a do this expression. We will have Q equals A square times star squared plus A B star. That's a long expression with 1, 2, 3, 4, 5, 6 different parts. This is just the size of the scalar value of Q. So in principle, we can say that Q is a linear function, linear in the sense that no H square and K square, they're just numbers, and it's only an addition. Q is a linear function of the reciprocal. This is the GII. Perhaps it should be a G star, but we can space metric tensor. Well, yeah, this is the expression, and indicate instead of A star square, we can just go to this matrix here, and this is the 1, 1 element. This is the 2 element. This is 3, etc. And there will be a factor of 2 here, but perhaps we can skip that factor of 2. That it will be part of the matrix element. So here you have a simple link with linear expression of the distance from a reciprocal space where terms of the HKL, H square, K square, HK, HKL, times some parameters that can call for cell parameters, but they are related. If we take G33, for example, it's related to the C star square, but it's still, we can call it a cell parameter. One of them, the G12 is related to A star, B star, and cosine of gamma star. Not more complicated, but it's still related. So sometimes the G parameters, they are talked about as unit cell parameters. This is what one calls a quadratic form. The squares and the multiples, but it's nothing plus H times something plus K times something. They are absent. At least there are quadratic terms. So, coming back to reality, we leave the mathematics, perhaps. This is Bragg law. Or if we slightly convert it, we can practice these or the Q in terms of it's related to the scattering angle, the 2 theta, but actually sine square of theta. So divide 2 theta by 2 and take the sine and square it. But it's also related to the wavelength, or I should say maybe the D star is the distance in related structure. It can't be dependent on the wavelength. But on the other hand, the scattering angle is dependent on the wavelength. So if you record the scattering angle, what to calculate D star, no, the wavelengths of the radiation. Otherwise, this is usually known. If it's not known, the wavelengths, and you know the unit cell scattering scattering angles of the diffraction data, and if you know what sample you have, then you know the D star also, and you can calibrate the wavelength. It is something usually done at synchrotron installation, because they have some monochromatic crystal cutting out all band of radiation. They usually don't have, in some devices they have continuous radiation, but very many devices have sharp lines, but still they have a width at least depending on the energy of the beam. So it may be useful to be able to calculate the wavelength. Using this Q, if you can see that sine squared theta or D stars square, they are proportional to each other. So you can construct either Q equals some expression of parameters, or sine squared theta, similar expression, but maybe we shouldn't use the same symbols. So G for values connected to the unit cell correctly, and maybe A for connected to the sine squared theta, but which in turn is also dependent. But it's the same expression. Yes. Yes. Yeah, but it's not strictly related to the units, reciprocal unit cell, but scale with the lambda. Yeah.
As a metric.
Geometrical, but it's only used for transforming vectors to another vector. Just a calculation made. There is a reciprocal metric tensor and also a real space metric tensor. The general expression for different crystal systems, for example, cubic, one can simplify it. So since the alpha beta gamma is 90 degrees, how is alpha beta gamma present? Alpha beta gamma. Here is cosine gamma, cosine beta, and cosine of 90 gamma star. Now let's see. Gamma is 90, then gamma star is also 90. Yeah, one of them is 90 minus. So cosine of 90, and then you have to remember your trigonometry, that is 0. Parts they disappear and make it angle. And also ABC is equal, so the 11 and 23 that equal. I can simplify the expression very much. This, which is quite convenient. And then at least if you do manual calculation, or if you're into programming. Otherwise, you don't need. Hexagonal system, for example, you only have the all angles are 90 degrees, but the alpha beta is similar. AB is similar, but not equal to C. Then that one, etc. Until in triclinic system we don't have any application. Monoclinic angles of 90 alpha gamma 90. how to solve for cell parameters. Only basic graphic concept. If we know, well, what do we know? We guess HKL, for example. In the cubic case, we can calculate. Suppose we guess for HKL, then we can calculate that one. And we know the Q value because that. Then we can solve for the. That is the way to solve for unit cell parameters in cubic case. It will be, I don't have the, but say that we have an orthorhombic case, then it's one of the rows here times the unit cell parameters, the first basic value, second one times the row column here, third row times the column. We know all of these HKLs because we have guessed them or have somebody know them, and we know the spacing value. We don't know the. This is the basic system. Similarly, continuing from all parameters to refine them. And we were discussing about refinement last course. Parameters. Some of these diagrams. We call it capital D. The parameter best possible or with best possible value minimum some of these diagrams. That is the least where some of the variables and it's variables where should this is exactly the same idea like other type of least square assignment. Try to find these parameters, minimize the calculated value they are dependent and maybe the alpha. So I'm how to find the minimum and make the derivative of that. In structure analysis, tricky equations tricky expression, but on the other hand, in simpler version, so we can take some. I only took these from cubic. The equation system, which is only one line, sum of all HKL and where it nearly very similar. Can go to maybe tetragonal. Here is a term that could be calculated from over all the HKL, HK and square, HK square, HK square, and L square, square 2 plus L. You get the, but this can be calculated from the lines that we have in there. And here are the unit cell parameters. This could also be calculated. H square and K square and multiplied by the different. And then knowing this vector and this matrix, then solve for the And it's tricky to do it. I mean, only the idea is because this is what is done in. And the figure merits then. The whole figure merit define like the M20 common version merit. Then we take the sine square theta of the 20th line and divide by the number of theoretical possible lines up to that line. Also divide by the average difference delta up to the end line. And if there are few theoretical lines, and if it's very small average error, then this will grow large. And the Wolf said now, so we can't ask it, but if it's better than 10, K or five. Similar to the Wolf merit, this we could neither F index, very similar, but instead of the things we keep them this is also better than 10 or more. Then it's unique. One can illustrate the merits. Schneider is perhaps not saying anything about what it has a unit here, but the Wolf also has a sine square theta, so one can say that the Wolf figure merit that enhances those enhances I figure. Pick it up. Yeah. And then the Wolf figure merit, if this is the observed pattern with some action line, and if we have two choices there, perhaps one of the choices is slightly different, that you can't see the difference, but this calculated unit cell doesn't fit very well. On the other hand, this unit cell fits better, but it contains a lot more diffraction line. Which one do you believe in? I would say this one with some, because from a distant view, very much like our observed pattern. If we can't explain all deviations by some mental errors, way, still, I would say that this one is simply better correspondent to that one, even though maybe that line is better coinciding with that one. But we have a lot of unobserved, which is why should there be a lot of unobserved? And we can choose pixel over cubic pixel over a million angstrom edge. The index, but it's rubbish. Structure with a million angstrom edge on the cube system, or we can probably put in random atom somewhere and also mimic diffraction pattern, but still it would be rubbish. Or glass maybe. I would say that here both of them are here defined because it avoid they take into account also the sine square theta of the high line, while and the low number of calculated, that is also present per Schneider. But here we will have a lot of lines, and the 20th line will be somewhere here, a low value of sine squared theta. So that effect that occurs in the denominator, the two. If they're high, then it's good. You have a problem if they are more than. They should be better. Then that's a fairly accurate correspondence. Observe.
Doesn't.
Yeah. Oh, yes, so
Sorry, doesn't. I see.
no. Yeah. Yeah, I would choose that one, but is Schneider also indicates. I would say that indicates how accurate the pattern measured, because the delta theta here actually that one. The number of theoretical lines are similar in both. At least that was the case. Maybe there are modifications by software. I know that the software expo that we will have a look at uses the Wolf figure merit, but also corrected or adjusted, or I don't remember what to call it. Here we have a cubic suspect. Computers believe that it is cubic because it has a few lines. So if it is cubic, then we know that u value be x squared plus squared plus. We know this. Oh, sorry, this is sine squared theta. Change only mental. What do we know? For the first one, it's the H1, K1, L1. Second one, it's the H squared plus A squared plus B squared times 10 L prime. Suppose we take and divide by 1. 16094 divided by 1. Then you need to go to your favorite program. Don't know if you have a favorite program. Doesn't work. Right, just slow. Så, nu ska vi se, vad skrev vi nu? 0,1698. 1609.8 divided by 0.06. 0335. 0335. Does this help us? Now, perhaps? These are the HKL. Then we can compute the sum of squares. 1, 4, 5. 2 squared is 8. 9. 9. Here you see the lines, they give exactly the same sum of square. So they will overlap in direction pattern. How can you express 2.6767 as the float of integral? And multiply by 2, no, multiply by 3, that is perhaps possible. Times 6 times 30, 8 upon. Is 8 and 3 available? Yes. But I would say that 0.06, 0.16 is the 111 reflection. And the 220 reflection. 0.2213. Or we can maybe go further. 8 square plus k square plus l square times k11 is the 1. The first times square theta, then we can solve this unit of parameter, and we can use that check all the other line. I think this will turn out to be able to fix. We need to remember that this was copper K alpha 1 radiation, then we will get that in A 5.43 ounce approximately. Silicon. That is the sine square theta. But instead we would, nowadays, capital Q, that is the sine square theta times 4 divided by lambda square to get it independent of valence. Just to realize what do these numbers mean. It's the scattering angle sinus square. Here it says that this was obtained with a well-calibrated Guinea Hegg camera, and I need to show this was our working horse here at Harvard some time ago, a very long time ago. Here they are. They were old when I came here. They were from the 40s, small camera cassettes like that. The advantage was that the amount of sample was very, very small. And for example, if you're into nuclear business, to analyze the radioactive waste material, then it's very convenient because it's very small amount, much smaller actually than we could probably do it if we are careful today. We are not routine. Routinely we use a lot more. Here you have another cubic subspec. If you want to see just by visual interpretation, this value, this is also sin squared theta. This is approximately twice that, 3 times as that, 4 times as, 5 times as, 6 times 7. No, it's something missing. It is 6 times the first one. And you see that 7%. Can't formulate that integer as a sum of squares, at least integer squares. But the values, I immediately recognize it factor 1 to 2. But this is the that's clock is 11:50. We are at final image. I have some suggestions for afternoon. I have 3 samples: silver chloride, silver oxalate, and unfortunately no more silver compound, but manganese oxide. Since this is a neutron course, we should perhaps have neutron-related samples. This is from the previous. Should we take lunch? Questions? Yeah, I should stop this recording.